Let's jump in very quickly here. We got a lot to cover. So I wanted to start by giving you a bit of an idea of what we'll cover today. So we're going to cover how GPU inference can address your organization's application and performance problems. Something about NVIDIA's deep learning software and inference options for both on-prem and in the cloud, and where and how you can get started with, for example, pre-trained models, scripts, and tutorials. And a lot of these are containerized for ease of use. But before we get into that, I really want to start with a bit of an overview to kind of set the stage on this. So up front, if you're not that familiar with deep learning, especially on GPUs, I just want to cover some of this. If you are familiar, my apologies. Think of it as a bit of a refresh. The deep learning workflow is actually a bit complex, and mostly in the industry we talk about papers and research and things, and that's really just the central part in this flow, which is the training. And the model zoo where new networks are created and tried and tweaked. But there, on the left, there are really important parts. For example, the data. You have to have massive volumes of data, and you have to have the right data, and the data needs to be tagged. So that's something that, in general, unless you're using a pre-trained network, that's up to you, and you have to bring that to the party. And that's really what makes your solution unique. That data needs to be pre-processed in some way. Maybe it's cleaned up, maybe it's tagged. There are a bunch of things that need to happen. Now let's talk about the actual flow, the training flow. Hugely iterative process. It can be millions or tens or hundreds of millions of iterations to explore and train and optimize networks. There's a deployment step, and this is really where taking that trained network and putting it to work and actually getting value out of it comes into play. And that's typically done with some sort of compiled runtime. It can be deployed within a framework that you trained in, but that's a fairly inefficient way generally. And then deployment at scale, things like Kubernetes. Platform to do workload balancing and really manage, adding and removing resources. So to really try to make this complex process simpler, what we've done is, we've taken some of these key parts of the workflow and containerized it and made it available on NGC, NVIDIA GPU Cloud. So, for example, we have optimized virtually all the frameworks and made those containerized, made them available to you. We have also made available containers with pre-trained networks for deployment and discipline-specific scripts or application-specific scripts. Those are available too to get you started and help you get moving faster. And then last, we have ways of, with TensorRT serving containers, we have ways of you being able to deploy, for example, in a Kubernetes environment and manage resources for scale-out inference deployment. So we're trying to make it easier and try to get you up to speed more quickly. I wanted to kind of talk about deep learning in production. What started out, the thing that really catalyzed this whole industry was money, oddly enough. So it was about making money, mostly about ad placement and search and recommendation for shopping. Incredibly important, paid for the development and the creation of this industry, but we've really moved beyond that now. There's an incredible array of uses. It's less associated with direct generation of revenue or profit and more associated with new ways of doing things, better ways of doing things. And the reason is it simply works better, faster, and it keeps improving. So I want to touch on a few really cool uses. Hopefully it'll be a bit of an inspiration for you. My apologies if you already know this stuff. Obviously, things like search and visual search, if you look at Google, Bing, Amazon, any of these guys, Baidu, they're all using deep learning. Speech, natural language processing and translation is all AI-based now. Smart cities, use cases for managing cities and monitoring, thousands to millions of cameras and sensors really requires AI and deep learning. Video image and video content detection, this is for live stream tagging of video things. You can think of a Twitch service, for example. How do people know what they're looking for? Well, an AI has to interpret the video stream and tag it. Medical imaging and diagnosis is being revolutionized. Pharma and pharmacology and drug discovery is really fascinating. It's an incredible area. We're seeing, a lot of molecular modeling happening with deep learning AIs. Drug interaction prediction is starting to happen. Drug design to bond to specific receptor sites is happening. It's incredible, blossoming in that industry. There are some really cool uses in industrial, IoT, industrial automation, and one I want to touch on is really unexpected, and it's very cool, and it gives you a hint on how radical you can adopt AI. In 5G, virtually all of the base station manufacturers for 5G have decided that with this massive array of antennas on a base station, and beamforming being really critical to frequency reuse and dB gain to directly create a beam transmitting and receiving with a cellular handset out there somewhere. It is such a complex problem that everybody has decided to use AIs to figure out exactly how to manage all of those beams at one time. So very cool and unexpected use, and when you get 5G infrastructure, you will be using AI. Robotics and testing, there's engineering use cases now we're starting to see. For example, semiconductor inspection. If you look at almost all the memory out there, flash or DRAM, and you think of the billions of memory sites, those are being inspected with AI. There's really no other way to do the accuracy and volume of checking. And then we're starting to see use cases in CAD, correct by construction design or design rule checking. And we're also seeing software, checking, debug, and even patch submission. And then I also want to point out very specifically in the HPC environment, if you have an application like this, it is perfectly designed for AI. In HPC simulations, you typically get time step increments, and you get all of the tagged output data. You know exactly what it is, and that is the perfect input for training neural nets. So we're starting to see a lot of things like protein folding, computational fluid dynamics, molecular modeling, generative design. This is all coming out of changing HPC to AI-based applications. So wanted to stop, just pause really briefly and give listeners a poll here, and please scroll down. We're wondering what of the following is the closest to your deep learning application. And there are a lot of options down here, so please scroll down, and then when you're done, scroll all the way to the bottom and submit. I'll pause for a second. And before I advance, I wanted to talk about the next slide, which will be neural networks and workloads and the various types. We're seeing a real explosion of neural networks. We talk a lot about CNNs. I think I'll advance now. We talk a lot about CNNs, which is on the left. But the truth is, this is important and interesting as that is, they're pretty simple networks. They're pretty, not that exciting a use case in a lot of ways. And most of the high value or really interesting networks tend to be over on the far right in the new species category. Things are emerging all the time. And if I look at, for example, current recommenders or ad placement engines, those are all in that category. So recurrent networks for temporally based decisions, GANs and reinforcement learning for more interesting robotics and IoT. So the point here is that networks keep getting more complex and they keep getting better at things. So if we continue thinking about CNNs, that may be a mistake. And I want to point out this growth in size and complexity. If I look at this chart, it's by design pretty simple, but it's accuracy versus network size. So and over time. So the networks are the size of the network is the bubble size. And the top right there is about 50 million parameters. It's a ResNet-like network. It's very high performance. It's about 40 gigaops per inference. But things are moving on. And if I look at what some of the papers or networks in production are, they're moving to more complex things like MOEs and that. And if I look at the latest papers, it looks like this. It is gargantuan. And the reason it's gargantuan is it just works so well. This is about 4 billion parameters. I've seen papers up to about 140 billion parameters. And some models are in production. Now I can think of 2 models that are about 2 terabytes. The actual model is about 2 terabytes in size. So models are growing in complexity, and this is to encode more information to get not only better accuracy, but more precision in results. So the point here is that not only are the networks growing, the compute required for every inference is growing exponentially. If I look at the throughput of the T4 GPU, which is our smallest data center GPU, and I compare it to a fairly high-end 2-socket CPU, which is the blue line. On the left is a vertical linear scale of inferences per second throughput versus batch size, and this is coming close to 10x throughput. On the right is the latency of an inference, and if I look at a real time, often defined as 2 milliseconds, on a CPU I can do 1 inference at a time and meet that goal. I can start batching up inferences with GPUs and get much higher throughput, and as well as I can start using tools that will load multiple inference images on a single GPU to get even higher throughput out of that resource. So, we can get higher throughput, lower latency, and have fewer hardware resources in the data center or the cloud to get your jobs accomplished. And just let me touch, we'll get to the software stack pretty soon, but one last thing is these are fairly high-profile uses of GPUs already in the data centers. So, for example, Bing doing search, they get about 60 times better latency. That means 2 things. One is they can do a better neural net search for results, and they can offer the result faster, so they get happier customers. Speech and voice, better accuracy, the capability of using the GPUs used to do a more complex network again, and so better results. Pinterest gets higher quality results more quickly, and so they get better user engagement, which equates to revenue enhancement. And then PayPal, on their fraud detection, they get better performance, but more importantly, they reduce their hardware infrastructure, their data center infrastructure by 8x to get all of their work done with fewer resources. The GPU software stack is very complicated. So there are a lot of interdependencies, and there are multiple hardware platforms that support GPUs, so software needs to run on different platforms. And I want to point out that while a GPU is the lingua franca of deep learning training, that didn't just happen accidentally. It didn't happen overnight. It was all built on more than 10 years of HPC, API, and software stack development that was built for supercomputers. And there were multiple hardware generations and architectural enhancements that happened to set the stage for that. And then the whole AI infrastructure was built on top of that. So starting at the bottom, there are hardware platforms available from NVIDIA and our partners, whether that's OEMs, ODMs, or cloud providers. There are, on top of that, there are software libraries and SDKs for machine learning, AI, deep learning, HPC, and graphics. All frameworks are supported, HPC and Workstation. There are domain-specific applications available. And the problem is there are integration and use challenges with this. So one thing we've done is to create NGC containers to help you package these, make sure they're tuned, make sure they operate well, and making them available. So an example is taking a slice through this stack, providing the drivers libraries, domain-specific libraries, and any of the frameworks, getting this prepackaged and available, and this is optimized, tested, and packaged, and will run on any of the platforms, and it's tested in the cloud instances as well. And we can go one step further. We have containers available that also go and extend into a specific use case, so a specific application, and these are packaged as well, so you can begin running with that. We even have pre-trained networks available so you can work with them. These containers are updated regularly to optimize performance. And we'll talk a bit about that in a minute, but first, another poll. And again, please scroll down, and then, once you've made your choice, hit submit. Do you use containers in your organization today? We're very interested to know that. And while you're doing that, I will talk about the next slide for a second. NVIDIA GPU Cloud, NGC, is really a container registry so that you can go there and download containers, and you can update containers as improved versions come out. There are more than 50 containers available. There are model training scripts available as well for specific use cases. I'm going to advance now so that there are pre-trained models available for you to begin working with or just use directly, depending on your application. And there are industry workflows available too. So this is, the whole point is to simplify your deployments, allow you to innovate faster and more reliably and predictably, and deploy anywhere you need to. So, interesting results. Most of you do not use containers today. Thanks. Maybe you should. Okay, so I wanted to talk quickly about one of the reasons for using our containers, and that is that we regularly update them, we regularly improve them. And here the point is just historical record. We generally improve the throughput of our containers about 2x per year. So with the same hardware, the same cloud instance, a year from now, you should probably get about twice the throughput that you're getting today. So there's a really good reason to update your containers regularly. Now, some of the software that's available, TensorRT is really our inference platform, and it minimizes latency and maximizes throughput for inference deployments. And this is, we really recommend this for especially scale deployment of inference. You can import models trained in every major framework. TensorRT will package that, compile it, optimize it, and then you can deploy in the data center at the edge, or even in automotive, for example, or robotics, embedded devices. It's about up to 40 times higher performance than CPUs. It will also import ONNX models. ONNX is the open standard for interchange between frameworks, so most frameworks can export ONNX as well. And it's available for download, again, either on its own or in containers. Um, a lot of people want to deploy within a framework. So, for example, TensorFlow is the most popular framework, and a lot of people just want to deploy inference within TensorFlow. If you do that, you're giving up an incredible amount of performance, and you're really impacting latency because a framework has a tremendous amount of overhead. We've worked very closely with the TensorFlow team, and now open deployment. It's available from us. It's available from TensorFlow.org, or you can download on GitHub. It integrates TensorRT, which I described, with TensorFlow, and it takes only a few lines of script to activate in the standard package, and the impact is profound. So, it will give you on order of 160 times the throughput and much, much, much lower latency than compared to running TensorFlow on a CPU for inference. So, again, really valuable. I would suggest picking up containers and deploying this way. Then TensorRT Inference Server is, or some of us call it TARDIS. It's a containerized microservice for data center inference. It's really for scale deployments. It's built on Kubernetes. You can add and remove resources dynamically depending on your workload. So really valuable for at scale, especially in the cloud. It can handle multiple concurrent networks on a single GPU, so you can fully load GPUs and keep them fully occupied, and to reduce the number of resources you consume. And it supports multiple frameworks: TensorFlow, TensorFlow and TRT, TensorRT, and Caffe2. NVIDIA GPUs are available on all the major cloud platforms, these and several others, and it allows you to get started easily. You can use it for development, you can use it for training, you can use it for inference. There are multiple platforms available from each of these cloud vendors, so you can also, they're tuned for development, training, and inference as well. So again, trying to make it as easy as possible. You don't have to use our containers. You don't have to use our software platforms. We think it's a good idea. But there are all of our partners, or many of our partners, also have services and platforms available that you can use directly. So they have a slightly different take on services to get you up and running fast, but incredibly powerful. And again, these are all built on top of NVIDIA GPUs. And then last, platforms for on-prem use on the left, highly specialized systems. This is things like DGX, DGX2. Our partners, ODMs and OEMs make similar products. We can package those in pods, like full rack deployments. Incredibly powerful. Many of these systems would have been on the top 10 HPC list 10 years ago. Unbelievable power. More mainstream products, things that fit in a normal data center rack, a normal enterprise rack. These are available from our partners as well. Not quite as capable, but still amazingly powerful. And then workstations available from our partners and NVIDIA. And again, some of these, varying in capability and power. Things like the DGX station is an amazing platform. Okay. Another poll question for you: where are you most likely to try GPUs for your application? And again, please scroll down and choose your appropriate answer, and then submit. So I'll pause for a second there. And I think I will proceed. So what we'd like to ask then is that, hey, go ahead and try your models on GPUs. You know, there's some links here and resources, and I'll show some more in the next slide. You know, if you want to just go directly and deploy some containers, link there for NGC. If you want to learn more about it, there's another link, and then obviously technical information from our developer website. You know, please go there. There's an amazing amount of information available. And then more resources for you to begin working with. So I wanted to also remind you that this is the first in a 4-part series of webinars. You know, there are a lot of resources here. They will be available after this webinar, so you can come back and check that. And I think with that, we're probably going to go to Q&A. Okay. So I have an interesting question. Does NVIDIA have a recommendation whether it's better to use a data science workstation with a GPU or leverage data center deployments with a server-side GPU? And I think that is, it really depends on the organization. It's incredibly convenient to go ahead and use a workstation and a very powerful way to do development. It is also great to deploy within data centers, and depending on who you are and you know what your budget is and how you work, they are both fantastic solutions. Especially if you're using containers, because you can deploy containers in either location. Some people prefer to develop in the cloud, and then when they deploy, it's just it's very seamless. So I think they're both excellent. Both excellent platforms, and it depends on your preference. See what. Let me check. Any advice on how to get started if we do not have AI expertise in our organization? I think probably the best approach there is to really try to define what problem you want to resolve, and then go to the containers repository and try to pick up some networks that seem appropriate to that problem. And if you can begin working with a pre-trained network, it may not give you the best results, but it'll let you experiment and try out the flow. So there we go. An interesting question. What approach is better to use, TensorRT or TensorRT and TensorFlow? And I think that this really depends. I'm going to give you a more complex answer. You probably want a yes or no answer, but a lot of people prefer to deploy within the same framework they trained in. Sometimes that's just a habit. Sometimes it's a flow issue. Sometimes it's a complexity issue. And you will always get higher performance and throughput and lower latency if you just use straight TensorRT. But there are some new and complicated networks that emerge all the time. And if TensorRT is not able to handle those well, Then working within TensorFlow, using TensorRT in TensorFlow allows any layers that TRT has difficulty with to execute within TensorFlow. So quite literally, anything you can train will in fact run with TRT and TensorFlow. So that's actually a compelling reason for a lot of people right there. They're both fantastic ways to deploy. What are some of the alternatives for DGX Station? You know, a lot of people, there are amazing options. A lot of people are quite happy just putting a GeForce card in a desktop for development. Some people go out and buy Titan V, for example, and use that for training, and it's stunningly capable. You know, you can start, you know, with a high-end desktop, something like a gaming PC, and work up from there. And then, of course, servers. There are multiple rack mount and tower servers available that have computational GPUs in them. So again, those are fantastic choices. There's an incredible number of options. What's the relation between TensorRT and containers? Okay, that's a good question, and it means I didn't do a very good job explaining, so my apologies. TensorRT is a software product that we use to compile, optimize, and tune trained networks for deployment. So when you deploy onto any sort of GPU, whether that's an embedded robotics GPU or a data center GPU, we wrap containers around that and the entire software stack that's needed to use it so that you don't have to worry about building that software stack yourself. So the container is a way to deliver that very easily to you. And that's true of all of our software products. You can use them on their own. You know, you're welcome to download them. But we do package them in containers so that it's easy to download, easy to know you're getting the highest performance possible, and easy to get the updates when they're available. So again, we're just trying to make it simpler. I hope that answers your question. Does NVIDIA GPU on AWS Cloud build on top of the NVIDIA data center? What's the relationship? So while we have an amazing data center ourselves, that's not actually what they are using or you are using. Amazon, for example, has an incredible GPU infrastructure. It's all theirs. NGC is actually a container registry. So you can go register and download containers, and those can be run anywhere. So they can be run on your desktop if you have a GPU. They can be run in AWS services. They can be run in Google Cloud or Azure or Alibaba or Baidu. So Amazon has their very own capable infrastructure to use. So I would highly recommend it, in fact. Let's see. What else do we have? Let's see. Which is the future roadmap for NVIDIA card optimized for AI? Do you have a plan for a new chip about it? Thanks. So broadly speaking, we don't talk about our roadmap, but what I will tell you is that V100 is still our premier AI and compute platform. It's an amazing, capable platform. It is the highest end GPU instances in most of the cloud providers, and it will be for some time to come. We also have Turing products, and those can be very capable in a workstation, but ultimately the Volta V100 is our premier compute platform. So for now, that's the guy. Let's see, what else? Okay, how does TensorFlow serving perform versus TensorRT for GPU inference? So again, we're going to have a deep dive on these topics in subsequent webinars, but again, this is my failure to communicate this clearly. TensorRT is, it's easier to think of this as something like a compiler. So TensorRT takes a trained network and it optimizes it and creates an executable for the GPUs. TensorRT, Tensor Serving platform is really a Kubernetes level data center management platform that orchestrates the workloads and will expand and contract the resources required and also do bin packing on GPUs of multiple inference packages. And those inference packages can be TensorRT, they can be TRT and TensorFlow, they can be other inference engines. So I hope that clears it up for you a bit. Another one, my concern with data center GPUs is their CUDA core density. Do you have any suggestion or advice on how much of an impact CUDA core count has on performance? It depends on the workload. So let me respond. It depends on the workload. For inference, we really developed the T4 because it is an incredibly capable inference platform. Inference typically takes less compute or less sustained compute for inference than for training. And so we developed T4. T4 actually can do a great job at anything that's compute-oriented. V100 has a substantially higher number of CUDA cores. More importantly, it has a higher number of tensor cores, which is where a tremendous amount of the actual compute happens. T4 also has tensor cores. It is able to do optimized compute on quantized values, so down to int 8 very efficiently. And again, once you have baked a neural net, once you've trained it, then you can quantize it a bit. And something like a T4 can take advantage of that. So there are multiple different types of CUDA cores. They're capable of different things. First order, the number of CUDA cores is proportional to the amount of compute that a GPU can do. Most of the AI compute is running in tensor cores, and so that's the really important component. Again, I hope that's an adequate answer. We're still getting a lot of questions. What is the relationship between TensorRT and cuDNN? cuDNN is a library of neural network optimized kernels. TensorRT is, so cuDNN is a programming API, essentially a set of libraries. TensorRT, it's easier to think of it like a compiler, and it has optimizations for certain constructs, and it will aggressively optimize and quantize and prune, and so they're one's for a programming environment, one's for compiling to an executable. I hope that clears that up a bit. What I said is not 100% true, but it's a good approximation. A lot of people are building using Titan RTX, and the claim is that it is as performant as other high-end cards. Any comment on that? Titan RTX is incredibly capable, and it is also very capable, especially at video processing. And it includes the special interest of Titan RTX for researchers especially, is that it includes the full Turing tensor cores, which means that you are also able to experiment with integer 4 and integer 1 operations in matrix math. So for a researcher, Titan RTX is super interesting. For for somebody just trying to bang out neural networks and train them or develop them, Titan V is fully equivalent, possibly better. Titan V is also better for HPC development. Again, I hope that clears it up a bit. They're both incredible products. Does NVIDIA GPU Cloud consist of NGC only, or is there other service that's similar to other cloud providers? So I want to be clear that we're not, we work very closely with our cloud providers. They are cloud providers first. They do a great job. That's what we support. NGC is really about providing the containers and making sure that they work exceptionally well, not just on-prem, not just in your workstation, but also in all the cloud providers. So we work very closely with them. I hope that answers that. I think I just got a comment more than a question, I think, which is improve Turing tensor cores for mixed precision scientific computing, double precision, floating point. Point taken. We like the idea. We're thinking about it. Stay tuned. Yeah, there's no question that the HPC community is getting very excited about tensor cores and trying to figure out ways to take advantage, and obviously supplying higher precision versions could really transform HPC. Can you comment on tools for pruning and quantization and various other compression techniques? There are a lot of issues with quantization and pruning, and typically it comes at an accuracy loss. The way a lot of people do this is to retrain. So they'll take a trained network, quantize it, prune it, and then retrain to try to get back some of the accuracy loss. Those are things that are there are industry tools available. There products available. A lot of people provide those for their hardware platforms. We developed TensorRT to do that kind of thing. We lose virtually no accuracy. So we typically lose like about less than 0.1% accuracy when we do the quantization and recalibration. So that is a relatively proprietary capability, and it works really well. And so that's why we recommend TensorRT. Let's see. What else do we have here? Can a card like a GTX 1070 Ti be used for development workstation? The answer is yes. Any GPU can, any of the GPUs we sell can support, the entire software stack. However, when you get down to a 1070 Ti, it will not be as capable for AI or deep learning for development. So just a warning. So you can do it. It's great. but it's not the most performant or capable platform available. We have any other questions here? Actually, a question here. How do you do model management? And I would suggest that's actually either a really simple or a really complex task. And so for a production environment, it may be as simple as there's just one model. So that it's a relatively straightforward thing. For researchers doing a lot of model development and hyperparameter optimization, there are flows developing for doing exploration. People keep what they call model zoos. And so this becomes a pretty big housekeeping thing. That is, I don't think there are any real standards for that yet. I think with that, I think that's probably the last of our questions, and I think we're probably done. Thank you.
Yeah, thank you for joining, everyone, and stay tuned for our upcoming webinar, and look for an email invite as well. Have a wonderful day.